When you look up at night and catch a streak of light cutting across the stars, you are witnessing the destruction of a cosmic fossil, a fragment of rock forged roughly 4.6 billion years ago. If you want to know how our solar system formed, you cannot study the Earth to find out. Billions of years of plate tectonics, atmospheric weathering, and a relentless biological life cycle have completely erased the physical records of our planet's own infancy. To understand the conditions of our solar system's birth, we have to look into the vacuum of space. Asteroids act as pristine time capsules, remaining frozen and untouched, preserving the chemical composition of the ancient solar nebula. Because the Earth has paved over its own history, reconstructing how our world was built means examining the unfinished leftovers still floating in the dark. The process began when a massive, cold cloud of interstellar dust and gas collapsed under its own gravity, flattening out into a rapidly rotating protoplanetary disk. Here in this disk, a distinct temperature gradient dictated the future of every object in the system. In the scorching inner regions, close to the young sun, only tough materials with high melting points like metallic iron, nickel, and silicate rocks could remain solid. Further out, past what astronomers call the snow line, the temperature plunged low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. If we zoom in on these solid particles, a process called accretion takes over. Electrostatic forces cause these tiny grains to stick together, clumping into centimeter-sized pebbles and then colliding to grow into massive kilometer-scale planetesimals. Throughout the vast majority of the young solar system, these massive chunks of rock and ice continued to smash together, eventually merging to form the 8 major planets we recognize today. But that natural progression stopped between Mars and Jupiter. Millions of these planetary building blocks stalled out entirely, permanently trapped as a field of floating rubble. That field of rubble is the main asteroid belt, occupying a region where millions of rocky bodies initially attempted to coalesce into a brand new terrestrial world. For centuries, astronomers hypothesized that this belt was a planetary graveyard, the shattered remains of a fully formed world named Phaeton that had exploded. But modern orbital dynamics have proven that the total mass of the entire asteroid belt is less than 5% of our moon. There was never enough material there to build a planet in the first place. The asteroid belt is a planet that never got the chance to be born. And the reason it stalled is Jupiter. As the giant planet rapidly grew in mass, its immense gravitational pull became a disruptive force that effectively patrolled the neighborhood. This model shows exactly how that disruption works. Jupiter's immense gravity acts like a tidal wave, injecting excess kinetic energy into the neighboring rocky planetesimals. Instead of gently merging, the rocks are forced to collide at high speeds, shattering upon impact. Jupiter's overwhelming mass truncated the growth of any nascent world in its neighborhood, grinding the rocky building blocks down into a field of aborted planetary components. Looking at this top-down schematic of the asteroid belt, you can see the distribution of rocks isn't uniform. There are empty gaps, known as Kirkwood gaps. These occur at specific distances from the Sun, where an object's orbit falls into a mathematical resonance with Jupiter. In these resonance zones, an asteroid receives a repeated gravitational tug from Jupiter at the same point in its orbit over millions of years. This cumulative stress eventually destabilizes the rock entirely, violently flinging the asteroid out of the belt and directly toward the inner solar system. Once that rock fragment enters the vacuum of space on a collision course with us, scientists classify it as a meteoroid. It travels through the dark, frozen, and completely silent. But the moment that meteoroid hits the Earth's atmosphere at roughly 45,000 miles an hour, it becomes a meteor. The intense ram pressure and friction from plowing through the air superheats the rock, causing it to glow incandescently and create the brilliant streak we recognize. While that journey accounts for asteroid falls, most annual meteor showers are caused by the Earth flying through the dusty ice trails left behind by comets. The bizarre exception is the Geminid shower, which originates from 3200 Phaethon, a rock comet that behaves like a dusty snowball despite being composed entirely of rock. By the time a fragment survives that initial eviction from Jupiter and the fiery gauntlet of our atmosphere, Less than 5% of its original mass actually strikes the ground. If it does, it earns its final name, a meteorite. Studying meteorites on Earth has a major limitation. The moment a space rock hits the dirt, it is immediately contaminated by our atmosphere and our biology. To see the chemistry of the early solar system as it truly was, we have to intercept these rocks while they are still in space. That requirement is why NASA launched the OSIRIS-REx mission to a near-Earth carbonaceous asteroid named Bennu. The goal was to extract and return a sample that has sat completely undisturbed in a vacuum for over 4.5 billion years. When chemists analyzed the Bennu sample, they found traces of minerals like halite and carbonates, indicating the asteroid once hosted an environment of liquid salt water. They also found all 5 nucleobases, the molecular structures that life on Earth uses to store and transmit genetic information in DNA and RNA. The chemistry inside the rock went even further. Out of the 20 amino acids utilized by biological life on Earth to build proteins, scientists detected 14 of them inside the Bennu sample. Because these molecules were completely protected from terrestrial contamination, the Bennu sample provides the strongest evidence yet that carbonaceous asteroids acted as primordial delivery trucks, crashing into the barren Earth to deposit the raw precursor ingredients for life. These discoveries shift the way we look at the sky. We are not separated from the chaotic, violent physics that formed the planets. The water that fills your cells and the organic molecules that weave together your DNA trace their lineage back to the payloads delivered by these ancient, battered rocks. When a meteor burns across the night sky above a forest, you're seeing the mechanism that allowed a barren planet to eventually bloom with life. By capturing and decoding these distant space rocks, we are reading the history of how a chaotic cloud of interstellar gas and dust coalesced into a world finally capable of knowing itself.